Hi, my name is Abhinandan Bharti, and this is gradient descent explained in 5 minutes. So, gradient descent is an optimization algorithm that is widely used in machine learning, specifically in neural networks. And optimization algorithms are essentially about maximizing or minimizing a certain function called an objective function, which in the case of machine learning is typically called the cost function, which is represented by j of theta. So, I'm not going to go into the specifics of the cost function today, as there are various types of cost functions. Okay, but instead, let me explain the idea behind it with an example. So let's say we have a data set of houses. Okay, we have information about the houses like the number of rooms per house, the square foot area of the house, and we have the target, which is a target feature, which is the price of the house. So let's say we want to have a neural network that can predict the price of the house given these other features. Okay, so maybe we'll have a neural network with neurons like so. These are the input neurons, the input layer. We have hidden layers over here in between. Okay, we have multiple of these layers. Okay, and maybe say this is the penultimate layer and this is the output layer. Okay, we'll have connections between the layers like so. Okay, and other connections like so. Okay, and eventually we'll come to the output layer, which is where we output the target price. Okay, so each layer in the neural network has parameters called weights and biases. Okay, and these are typically randomly initialized, must be updated over time. Okay, so initially our, our neural network is untrained. Okay, so if we give it an input, okay, give it a feature, a few features of a house, like a house with 2,000 square foot of area, maybe 4 rooms. While we know that its price would be around 500K from previous data, okay, a neural network which is untrained might output a value like say 100K. Okay, and this is clearly wrong. Okay, there's a big difference between the target, between the actual value and the predicted value. This difference is a representation of the cost function. Okay, we can say that the difference is around 400K, so maybe the error is 400K. Either way, the cost is really high in the beginning and we want to minimize it. So how do we go about with that? So to minimize the cost function, let's try to visualize it, okay? And this is, by the way, where we use the gradient descent algorithm. So we could have a convex cost function like this, okay, where the minimum of the cost function is over here, and we start over here, we make our way down slowly and gradually, okay, in small steps, which we refer to as the learning rate, okay. But this is only if we have convex function. We may have a non-convex function like this, where this may be a local minimum, but this is a global minimum. So if we start here, we may end up going to this local minimum, or if we start here, we may go here, even though the global minimum is here. So the objective of gradient descent in a non-convex cost function would be to arrive at a local minimum within the neighborhood, within a certain neighborhood in the graph. And just to comment about what I said about the learning rate over here, learning rate is typically a very important factor. Okay, we need to make sure that the learning rate is not too high. Okay, if it is too high, we may fail to converge. Okay, the learning rate, it'll basically bounce around in this graph like so. Or if it's too small, the processing time would be too long. It would take too long to actually converge. So let's take a look at what gradient descent actually looks like in practice. So this is a more accurate representation of gradient descent. Okay, we have these various hills, we have the valleys here, okay, like here and here, and eventually we want a gradient descent to converge and reach this valley over here. So let's take a look at the actual algorithm behind gradient descent. So this is a weight, okay, a parameter, okay, called theta j. Okay, we want to update theta j by using this formula. So this is the learning rate, okay, multiplied by the partial derivative of the cost function relative to theta j, okay, and this gives us the updated value of theta j. And just want to briefly touch upon the various variants of gradient descent. So what we have first is batch gradient descent, where the updates that I mentioned in this slide over here. Okay, these updates are applied after we compute the cost for every single example in the training set. Okay, so we get something like this. After one update, we reach here, and another update, and so on. Because this applies to the whole batch of training samples in the data set. This is why it's called batch gradient descent. This is typically quite computationally efficient, but it takes a lot of time. It's very slow and needs a lot of memory. On the other hand, we have something like stochastic gradient descent, or SGD. This is typically a much faster method of gradient descent. Okay, it is easier to fit the data in memory, and it is it's more time efficient essentially. Okay, the problem is, however, it is very noisy. It is a bit difficult for this algorithm, for this SGD to arrive at the point of convergence. Okay, so a good compromise between the stochastic gradient descent and batch gradient descent is what we call many batch gradient descent, where we use small batches of say 16 or 32 or some other small number, okay, and we apply, we essentially update the weights and biases after we evaluate the cost on a small batch. This is relatively efficient, fast, and generally stable and converges quite quickly compared to stochastic gradient descent and batch gradient descent. So this is what it may look like. All right, so that's the gist of gradient descent, and thank you for watching.